Okay. Now, very quickly, we recall how the electronic levels of a molecules are formed. This is a topic that is described already in the college when you study chemistry at the college, and you should have reviewed this in general chemistry courses, but we recall it in order to make it clear. Say, for example, that you want to study the hydrogen molecule. This is the simplest case of homonuclear biatomic molecule. Okay, so this is a molecule that is composed of the same two atoms, hydrogen, and that is formed by combining them. The level diagram depends on the energy levels of the two constituent atoms, and you can use a model that is named LCAO, linear combination of atomic orbitals. Okay, so think that you have two hydrogen atoms that are very far from each other. Then you know that the electron in the hydrogen atom is in the 1s state, is here. So the hydrogen is in the 1s state. Since the two hydrogen atoms are very far from each other, you can think that they don't speak each other. They don't know each other, okay? So they can stay both in 1s state. Now, when you take these two atoms and put them one close to the other, next to the other, and the distance is very small, what does it happen? It happens that you would have two electrons with the same spin in the 1s state, and the Pauli principle says that that's not possible. Okay? So what does happen is that the energy levels, of the two atoms, they combine and they give rise to two molecular orbitals, the 1 sigma and the 2 sigma star. Okay? So the H2 molecule is characterized by some energy levels. The lowest energy level is the 1 sigma, and the first excited level is the 2 sigma star. Since when you have these molecules, you have two electrons to put on your molecule, these two electrons will sit on the ground state with a spin up and down. Okay? And you preserve the Pauli principle. Okay? Now, what is the nomenclature that you use? Sigma, it means an orbital, okay? That is the combination of isotropic orbitals. The 1s orbitals, they are spheres, okay? So sigma comes from the combination of these spheres. And what does it mean, the star notation here? Now, if you watch the lower level, the 1 sigma, then you discover that the dependency of this energy level, the position of this level in energy, with respect to the distance of the two nuclei, has a behavior like this, okay? So if the nuclei are very close to each other, the energy of this level increases a lot, it goes up. If the two nuclei are very far from each other, this energy level is at 0 level. They don't speak each other. And there is a position when the energy of this level is at a minimum, okay? What is happening in this orbital? Remember that how do you get the orbit, the molecular orbitals in the so-called linear combination or atomic orbitals? You are combining the orbitals of the 1s levels. In this state here, you are combining the two orbitals with a plus sign. You're making a linear combination with a plus sign, okay? So the orbital that comes out is an orbital like this. What does it mean here? That the probability to find an electron the probability to find an electron is given here by the orbital, okay? And that's given that you combine with the same sign, the two orbitals, here they are not designed because the lines would be too close to each other, but the probability is different from 0 to have an electron here in the middle, in between. So you can have electrons here in the middle. If you watch the excited state, how do you get this orbital? You combine the 1s orbitals with a minus sign, okay? That means that the wave function of this side is positive, the wave function on this side is negative, and there is a plane where the wave function is 0. So you have 0 probability to find the electron here. As a result, what does it happen? It happens that in the first case, you have two nuclei, two protons that are repelling by Coulomb repulsion. They are pushing far due to Coulomb force here, but you have some probability to have the electrons in the middle, and these electrons keep the two nuclei together. They bind the two nuclei. Vice versa, in this case here, there is no probability to have the electrons here, and therefore these electrons do not keep the nuclei together, and it means that this orbital here is not stable. The two nuclei will repel. And in fact, if you watch the distance dependency of the energy of that level, this is always decreasing function. Okay? So, for example, what does it mean? It means that if you have the electron that is in this orbital here, the two nuclei will tend to repel more and they can separate. You will tend to go down along this energy curve and get to the maximum distance. But if you are in such an orbital, okay, the electrons will keep the nuclei together and there is an equilibrium distance. The equilibrium position is this one, where the molecule is stable. Now, this orbital here, the 1 sigma, is called a bonding orbital. It's an orbital that makes that if you have an electron in that orbital, it will help to stabilize the molecule. The sigma star orbital is an anti-bonding orbital. If you are there, the molecule will dissociate. Okay? So, the interaction between the two atoms is due to Coulomb repulsion between nuclei, Coulomb repulsion between electrons, and Coulomb attraction between electrons and nuclei. Given that here you have two electrons in the bonding states, the H2 molecule is stable. It survives and it stays in that state. Okay? This curve here of the bonding is named the Morse curve. Okay, it has a typical minimum here around here. And remember, this is the distance between the nuclei. We are in a very simple model where we have two nuclei, two protons, and so it's very simple to identify the distance between them. Now, what does it happen in the next most simple molecule, that is helium, molecular helium? It happens that when you take the two helium atoms and you put one next to the other, their orbitals combine and they give you the 1 sigma and the 2 sigma star. When you put the electrons in these orbitals, there will stay 2 electrons here and 2 electrons here. And then you will have 2 electrons in the bonding orbitals, 2 electrons in the anti-bonding orbital. And as you see here, the energy of the anti-bonding orbital is larger than the energy of the bonding orbital. As a result, the molecule is not stable. The two anti-bonding orbitals tend to dissociate the molecule more than the two bonding orbitals tend to associate the molecule. As a result, the two helium atoms will split and you will end up with atomic helium. Okay? Clearly, if you ionize helium-2, then you remove one electron from the anti-bonding orbital and helium-2 ion is stable. Okay? Now, this is the simplest case, homonuclear biatomic molecules. Now, you can go to larger molecules like oxygen or fluorine molecules. Okay? For example, in oxygen, you have that the last occupied orbital, they are the 2s and the 2p. The 1s makes a closed shell that is a core shell. It is untouched by the by the bonds, so you don't even write it here. And then you can combine the orbitals of two oxygen atoms and generate the molecular orbitals. What are the rules that you use? The atomic orbitals that pertain to inner shells do not combine, so they remain unperturbed. Okay? Only the orbitals with the same energy can combine. So you see here the 2s and 2s, they interact and they generate the bonding and anti-bonding 1 sigma and 2 sigma star orbitals. Okay? And you see here the 2p and 2p, they combine like this. Okay? Now, in the case of oxygen and fluorine, the two groups of molecular orbitals do not overlap. You see that the 2s orbitals combine and they give a group that is separated by the groups given here by the 2p levels. Okay? Now, you see that the symmetry of the molecular orbital can be sigma or pi. Okay? You remember that if you have a p orbital, you can combine the two p orbitals like this and you get a sigma, and you can pair like this and you get a pi bond. And this is written here. And again, you have bonding and anti-bonding orbitals. Okay? If you go from oxygen to fluorine, what is the difference? It is 2 extra electrons. Okay? And even if you have 2 extra electrons, fluorine is stable as a molecule. Now, what does it happen if you have biatomic molecules that are a bit more complicated, like lithium, beryllium, boron, carbon, and nitrogen-based molecular biatomic molecules? Then, in these cases, the combination of the orbitals is such that you have a combination of 2p and 2s. There is a mixing. The levels are not anymore grouped in groups. Okay, but the situation is similar. Then you will dress your molecule with the electrons, and by calculating the energies, you know if they are stable or not. In general, if you have heteronuclear biatomic molecules, like hydrogen fluoride, hydrofluoridic acid, no? Then the two, and you will combine the 1s with the 2px, you can have a bonding and anti-bonding orbital, and you will see that the electrons are here, and so the molecule is stable. And there are used to calculate the molecular orbitals. But in general, you know that there are symmetries, okay? So these orbitals, they have symmetries. They are sigma, and they are pi orbitals, and there are symmetries. Okay. For polyatomic molecules, the situation is much more complicated because you have many nuclei, of course. You can find the energy levels by the same approach, but of course the calculation is much more complicated. And the orbitals, they are extended all over the molecules or are localized in some portions of the molecules. It depends on the molecule. Okay. Now, so let's always keep in mind that when I have a molecule, it has the orbitals that may have a symmetry. Okay. Now, but this is only qualitative. Now we want to understand how I can use light to study the energy levels of a molecule, to understand what is the configuration of energy level of a given molecule, like this. Okay. So how do I perform my measurement? I use the so-called optical spectroscopy. In optical spectroscopy, I let the molecule interact with light. Okay? So say, for example, that you have light with a given spectrum that it is composed of monochromatic components with different frequencies. So you have light with frequency corresponding to blue, to green, to yellow, to orange, and to red. Okay? So you have a beam of light, of white light. For example, the beam that was produced by the lamp that you used on last Thursday in the laboratory. That was white light. Okay? Then you take this light and you send on top of a sample. Okay? And for example, you can think that your sample is constituted by some molecules that are in a liquid, in a solution inside a liquid. You have a container, okay? And inside this container, you have a solution of a liquid where you dispersed some molecules. For example, you go at home, you put water to boil on your kitchen, then you take a tea bag, you put tea inside your boiling water, and the boiling water will extract chlorophyll from the tea bag. You remove the tea bag and you get a brown-green solution. These are chlorophyll molecules inside water. Okay? And if the concentration of the molecule is small in water, you can think these are isolated molecules inside your solution. Okay? Then you send light to your sample and you measure light that is transmitted by the sample. And what will happen? You will see that in the transmitted spectrum of light, there are some wavelengths or some frequencies that are missing, that are not anymore there. What is the reason of that? The reason is that the molecule can be characterized, by energy levels, okay? So when light is sent on your molecule and it has the right frequency, it can be absorbed by the molecule. And then the molecule, once that it has absorbed it can either re-emit light or it can dissipate the energy. So in the transmittance spectrum, you will miss the light at the frequency that has been absorbed. Okay, so you will see some holes in the transmitted spectrum. Okay, now I have a question for you. That is the following. Think that you have in this sketch here, in the green range here, you have 1 million photons, green photons per second, no, arriving here. Then they excite your molecules. These molecules absorb the green photons, okay? And then it is very clear for us that when the molecule is excited, it can relax to the ground state, for example, by generating heat. Therefore, the photons that have been absorbed, say that, for example, you absorbed half of the photons, 500,000, these are lost, and you will miss them here in the transmittance, okay? That is the reason why you miss the photons. Okay? But now I ask you the following question. Say, for example, that chlorophyll is absorbing light, okay? And say, for example, that to relax, it emits again light at the same frequency. So we do this, no? Light is absorbed, and then you re-emit light at the same frequency, for example, in a very simple case. Then, if light is emitted, I absorb half of the photons, but they are emitted again. So in transmittance, I should see the sum of those that were not absorbed plus those that are emitted again. So I should have again 1 million of photons. Why do I see anyhow a hole? I continue seeing the hole. Why is there light that is missing? Remember, the spontaneous emission is isotropic. So you have photons coming from this direction and you are collecting from this direction. If there is no sample, you collect 1 million. Okay? If there is absorption here and light is then re-emitted, it is emitted in all directions, but you are collecting only along one direction. So these 500,000 that are absorbed and then that are emitted again, they are emitted in all directions, and you collect only along one direction. That is the why you anyhow miss the radiation. Okay? So you can have molecules that are emitting light or that are dissipating the energy. Anyhow, you will see the absence of some energy here. This is named absorption spectroscopy. There are some other types of spectroscopies. There is, for example, the luminescence spectroscopy. What does it happen in luminescence spectroscopy? Here, you send light with a given wavelength, with a given energy. The material is excited, and then you see that they appear, different frequencies in the spectrum. What is the origin of that? The origin is that with the excitation light, you are, say, bringing the molecule from the ground state to some excited state here. And then once that you are here, you can relax to this state or to this state by emitting light. So if you send energy and excite a molecule to a large excited state, then it can relax to lower state. And each time that it relaxes, it emits light at a characteristic frequency. So what you are seeing here, these are the frequencies corresponding to the transition energies of the levels of the molecule. So you are performing a so-called luminescence spectroscopy. Okay? Or it may happen also that you send light on your sample at, we were discussing with a colleague of yours here in the room during the interval. You send light at a certain frequency and you get that light is scattered or diffused at the same frequency, but also at different frequencies, as it happens in Raman. So you get the generation of new frequencies. Now we shall discuss, first of all, absorption spectroscopy, and then during the next lectures, we will go to luminescence spectroscopy, and then sometime to scattering spectroscopy. Now, what does it happen therefore in absorption spectroscopy? If you have a source of light that is characterized by a certain spectrum, when as not is the, say, intensity of light as a function of frequency. No? You send light on a set of molecules that have all the same levels, then if this molecule is characterized by certain energy transitions, say, for example, between E0 and E1, or from E0 to E2, you will see that these photons will be absorbed, and you will miss here the photons at that frequency. The same, you will miss photons at this frequency. So you will see holes in the transmitted spectrum corresponding to the transitions of the molecule. And of course, the frequencies that are missing are given by the difference of the energy states divided by the Planck constant. And therefore, you can measure the transmitted spectrum, you can measure the incidence spectrum, the input spectrum, and you can define a quantity that is named the transmittance, that is given by the transmitted spectrum divided by the input spectrum, the ratio of the two. Okay? Clearly, if ST is equal to S naught, the ratio is 1 and the transmittance is 1. Of course, since both of these have a frequency dependency, the transmittance can be frequency dependent. Okay? Now, in all the discussions that we shall make in the next, except during the laboratory work, then we shall go back to this. Clearly, when I study this process, there might be a reflection at the interface here. There might be a reflection at the interface here. We saw with Fresnel that but we neglect these effects. So when we study, when we are discussing absorption spectroscopies, we are neglecting the interfaces. In the experiments that we shall make, we will go back to this and take them into account. Now, if you take a typical liquid, for example, dichloromethane, that is in the liquid state, and you measure the transmittance of dichloromethane, and here you have the wavelength in nanometers. And so from 860 to 1660, if we are here in the near infrared, remember that the visible gets up to 780 nanometers. The dark red is 780. So we are in the near infrared here. And the transmission spectrum is characterized by a frequency dependency. You see here, this is 100%. That means you can measure transmittance in percent. 100% is transmittance 1, of course. But you see that corresponding to certain wavelengths, the system doesn't transmit. Here there is a very sharp dip, and you go down to less than 20% transmittance, and so on. But you realize that the situation is different from what you expect. That is, in a very simplified model, you would expect to have absorption only if light is at frequency nu1, because it must be, the energy must be exactly equal to the difference of these two levels. Okay, so you would expect to have that only the frequency nu1 is missing, but you see here that these lines are rather broad, they are broadened. Okay, so there is absorption not only at this frequency, but also around this frequency. So this situation in reality is much different from the theory. And the reason is that you can have that your excited state has a certain lifetime. So the energy of this state here is not exactly defined, but it is a sort of a small band. Okay? So if this is a small band, transitions from here to here, they do not happen to a single frequency, but to a range of frequencies. And the same for the ground state. You can have Doppler broadening of the levels. That means molecules that are traveling inside your solution, this is a liquid, they are going towards the light or they are going far from the light, and there is a Doppler shift. That is, the effective wavelength is different. This makes that the lines are broadened. You can have that the molecules are interacting with the environment. For example, they are hitting the wall. And the molecule that is hitting the wall has energy levels that are distorted. Okay? And that means that really the molecules are not all identical to each other, but they have levels that are slightly dispersed. Or it might be that this dip that you see here is the superposition of different bands. You see here that you have two peaks that are merged. Here you have many peaks, maybe that such peaks are so close that the peak that you see is the envelope of more than one peak. Okay? And you see here that these bands can be even very large. So when you work with real molecules, it is really very hard to compare the spectrum that you get with the theoretical spectrum that you expect from the structure of the molecule that you can calculate with any chemistry software. Okay? And so very often you do not have sharp lines, but you have broadened peaks. And this must be clear. Okay? So when you study atoms, for example, if you take a sodium atom in a low pressure sodium lamp, then the absorption and emission lines, they are very sharp because you are studying sodium at a very low concentration, and the comparison between theory and experiment is really very good. When you study light atoms, hydrogen, oxygen, and so on, that's it. But when you study heavy molecules, this is really light. There are even heavier than this. Then you will see the more and more such things. So rather than transition lines, you see bands in organic molecules. You see very large bands, and we shall see this. Now, let's go back to the small introduction to the energy levels that we gave above. For example, we studied molecular hydrogen, no? And we said this state here is bonding, and we call it gerade, symmetric. And the excited state here is antibonding, or ungerade in German. Okay? Now, clearly this is a very simple molecule, but in general, if you have two states, okay, and one is gerade, is symmetric, and the next is ungerade, you ask yourself, may I have that light interacting with molecule promotes one electron from here to here? This is the question. there are some selection rules, and the main selection rule comes from the Fermi theory. Now, in the Fermi golden rule that describes the interaction of light with the molecules, the molecule is described as a dipole, okay? And it is a first order approximation. It is very robust as an approximation. It works very well. So to say have situations in which this rule is not valid, you really need to go to very large intensities of light that normally you don't have in microscope. Okay? So in the frame of this model, the probability to have a transition from a state to another state is given by the expectation rate of the dipole moment between the two states, the arrival and the departure. Okay. Now, what is the dipole moment in classical physics? Is the charge times the separation of the charge. You see here, the charge of the electron minus E times how much the charge is separated. This is the same in quantum mechanics, because if you remember, in quantum mechanics, the position operator is the same as in classical mechanics, is R. So the dipole moment also, the operator is this one. And you see that this quantity is anti-symmetric. If you exchange R with minus R, the quantity changes sign. So this is an anti-symmetric operator. So what is this calculation here in quantum mechanics? This is the Dirac formalism. This calculation is the integral of the conjugate of the departure function times the operator times the arrival function integrated all over the volume. Now, if the parity, if the symmetry of these two states is the same, and if your operator is anti-symmetric, when you calculate the integral, you are multiplying one symmetry times an anti-symmetric times the same symmetry, you get an anti-symmetric quantity. And when you integrate, this will average to 0. So in the Fermi model, the probability to have a transition between two states which have got the same parity is 0. This is a strict selection rule. So you cannot promote an electron from a state which has got, for example, a Gerade parity to a state where you get a Gerade parity with light. In order to have a transition between levels, the parity of the start and arrival state must be opposite. So you can go from a Gerade to an ungerade state, but you cannot do it between two Gerade or two ungerade states. Okay? So the starting and arrival state must have opposite parity. This is the second selection rule. Because the first selection rule is that the energy of the photon must be equal to the energy difference. Okay? Now, there is another rule that you have to fulfill when you get an excitation of a molecule. The rule is that if you have a molecule in a certain state, by means of light, you can excite the molecule. Say, for example, take one electron and bring to an upper state. So you go to this condition here. An electron is promoted to an upper energy level. But you do not have to change the total spin of the molecule. So light cannot change the total state of the molecule. Given that in the ground state, all molecules are in the singlet, so-called singlet state, the total spin is 0, because you remember when you build the molecule here, the electrons that you put, they always pair to get spin 0. Okay, so in a ground state, in the lowest possible state, the total spin of the molecule will always be 0. Okay? Then when you excite with light, a process where light is promoting one electron to an excited state while preserving the total spin, so remaining in the single state, is permitted. But a process in which you excite the electron and flip its spin, because here the total spin is not anymore 0, but it is 1, okay, then this process is forbidden, okay? And this type of states of the molecules, they are named triplet states, because you are in a configuration of the spin where you are combining with the same direction two spins with 1/2 value. Okay? So you cannot have transitions that are governed by light in which you change the spin of the molecule. Okay? So when we shall study in the next slides absorption processes, we have to keep in mind that energy of light must be with energy that must be equal to the energy difference. The parity of the states from which you live and where you arrive must be opposite, and you have to preserve spin. These are the so-called selection rules. Now, what time is it? Let me. Let's have a 10 minutes stop and then we go ahead, because this is a change of topic, and then we can have a break, 10 minutes break. Are there any questions? No. The body is dead.